Alright, hello everybody, this is Ms. Pikarski. We're starting our Unit 4 on polynomials. There are several key terms that you need to know about and you need to know the definitions for. So I'm hoping to be able to go through this fairly quickly. Most of this stuff you'll have stuff that's in bold like this. Well, the reason why it's in bold is because on your paper it's blank. So you should have anything that you see in bold, check your work. See if you need to write that down. Okay, there's also stuff that I'm going to fill out over here. These terms are specifically for polynomials. You'll use some of these terms in other units as well, but we're going over all of them in this polynomial unit. Alright, so once we fill out all of these terms, we will be cutting out the terms on the dotted lines and putting them in our dictionary portion of the notebook. Okay, so we should be getting a lot of sections in that notebook filled out. Let's go ahead and get started on this. The first term or vocabulary term is just your constant term. It's the term in your polynomial where you're not multiplying by a variable. Okay, it contains no variable. So in this example here, your 3 is a coefficient to x squared, negative 4 is a coefficient to x, and 1 is your constant term here because you're not multiplying by any variable. Okay, so in this case the constant term is 1. If you do not have a constant term, then your constant term equals 0. Okay. Next term is called a cubic function. We've kind of covered these already. You've seen them, and it's just a polynomial with the highest exponent is a 3. Okay, so this is an example of a polynomial. I think on your notes you just have this equation here. You can see right here I have the actual graph of it. Let me make that a little bit bigger so you can see it. So this is what a third degree polynomial is, or a cubic function looks like. If you can, just give yourself a x and y axis, sketch this graph on your paper. You know, it goes up and it goes down. Or I guess it goes, yeah. Anyway, alright. So we will come back through once we get towards one of our terms towards the bottom. We will come back through and look at these graphs again. So go ahead and trace them out on your paper now. The degree, whoops, I forgot that I had it on select instead of pin. Let me go back to pin. Alright. Our next term is the word degree, and it's just the highest exponent used in the polynomial function. Okay, so if you have this equation here, your highest degree is 2. So this polynomial is a cubic function. This one, your highest degree is 7. Now notice most of the time your highest degree polynomial is up front, but it doesn't have to be. So pay attention to your order. Just because a term is out front does not mean it's your highest degree. Okay, in this case my highest degree is 7. When you guys are writing your answers out, I do want the exponents in descending order. That's the more proper form of polynomials, but sometimes you'll see them in in the wrong order, I guess. Usually they put it that way just to see if you'll get tricked. Alright, this one, your degree is 4, so it's a 4th degree polynomial. Notice you don't have exponents here, so your degree is 1. Okay, and again, your degree is 1 here, because if you don't have an exponent, it's just a 1. Now notice here I don't have a variable. Well, I could, and it would be x raised to the 0 power. So the degree is 0. And honestly, this is not really a polynomial. Okay, but you can at least see the degrees. Okay, so the degree is just the highest exponent. Your leading coefficient is the number that's attached to or multiplied to the variable with the highest exponent. So in this case, in this example, your highest exponent is 3. So the coefficient, or the leading coefficient, is negative 2. Okay. So if you remember about our transformations, the leading coefficient in this case would be your a value, and it would be -2. Alright, so hopefully you've got all those notes down. Let's look at the next page. There's a lot of stuff on this page that you need to fill out. Okay, maximum value and relative maximum value. We've already covered maximum values. It's the highest point on the entire domain of a function. Relative maximum values are the highest point in a particular part of the graph. So in this example, this would be your absolute maximum value, the highest point in the whole function, the whole domain. But this one is also a maximum point, and we'd say it's a relative maximum point. So in this case, we have two high points. Okay, minimum values and relative minimum, same thing, but lowest point on the entire domain and lowest point in a particular section. So this would be a low point, that would be a low point, and this would also be a low point. I know you can't really see these words too clearly. This just says absolute minimum, and these are relative minimums here. Okay. Polynomial functions. So this whole unit is about polynomial functions, and we're just now getting to the definition of a polynomial. And this is the math definition of a polynomial. I will let you read over it and fill in all the blanks because there's a lot of blanks. It's the sum or difference of terms that have variables raised to positive integer powers, which have coefficients that may be real or complex. We'll talk about real and complex later on in the unit. In polynomial functions, variables are not in the denominator. Okay? They're also not under square root symbols or in the exponent. Okay? So we've talked, last unit was about power functions, and we talked about how you could change your power function to if you had a square root, your power would be raised to the 1/2 power, and if you had a fraction, it would be x raised to the -1 power. Okay, so those can all be included in the power functions. With polynomials, you can't have a negative exponent. You can't have any of your variables under a root or a radical, and you cannot have a variable in the denominator. Okay, none of those examples are polynomials. All right, in general, polynomials can be written as this really weird, complicated equation. You've seen polynomials all over the place. Once you get used to it, they're very easy to recognize. Let's see where ck, what is k represented? Any real number constant, and n must be a whole number. Okay, most of this is not going to make a lot of sense to you. Okay, we've already looked at several examples of polynomials. Right here, this is a polynomial, this one's a polynomial, this is a polynomial. These are polynomials. Okay, this is not a polynomial. You need to have, let's look at the definition again. Let's see, sum or difference in terms of variables raised to a positive integer just means whole number, a positive exponent or power. Okay. 0 is neither positive nor negative. Okay, so if the degree is 0, it's really not a polynomial. All right, let's move on. I think we've covered what polynomials are. Most of you are very familiar with your quadratic functions or quadratic polynomials. It's an equation includes only second-degree polynomials. Here's an example of one, and I think I was planning on graphing it, but I don't think I did. In this case, it's a second-degree polynomial. It looks kind of like that. The reason why I know that it's going up is because my leading coefficient is positive. I'm not sure exactly where on the x-axis this would be. Let me see, 7/2. Yeah, I was going to try to put the graph on here and with the x and y axis, but honestly, I'm not going to be able to do it in my head while I'm doing this video. Sorry, I know some of you are disappointed, but in the interest of time, we're going to move on. Alright, so basically, that's what a quadratic function looks like. You've seen them a million times already. Quadratic functions, we've heard this word before. All it is a polynomial with a degree of 4. Okay, here's an example of one, and yes, I know your paper has a formula right there. I put that formula there because it was in the notes, but then I graphed it, and I really didn't like that formula, so I graphed a different quartic formula. So on your paper, just go ahead and cross out the equation that's on there, write this equation down, and then just sketch this graph. Just a rough sketch. It doesn't have to be super accurate, but go ahead and give yourself an x and y axis, okay? This is an example of a fourth degree polynomial. Whoa, I keep forgetting when I have my selection thing. Sorry, guys. All right, let's go back. There we go. All right, multiplicity. That's a word that you may not have seen or heard before. Essentially, it just means the number of times a given polynomial equation has a root at a given point. Okay, so we know that roots, at least I hope you know, that roots is another word for zero, which also is another word for solution. I'm going to try to fit this all in, which is also another word for x-intercept. Okay. E-R-C-E-P-T. I don't know if I don't believe I've defined the word root, mainly because I'm just, for the definition would really just be a whole bunch of similes? No, synonyms. That's the word I was thinking of. Sometimes you'll see the word root, and just tell yourself, okay, root is the same thing as an x-intercept, and it's the same thing as a zero or a solution, okay? So let's look at our graph here. Whoops, that was not what I was planning on doing. I wanted to make this bigger. Let's see. Nope, I can't make it bigger. Never mind. Just kidding. All right, so let's look at this. So we have this equation here, and notice this is in factored form of a polynomial. It's not written like this, how you have everything multiplied together and it's all one big, long, crazy equation. It's factored form. Notice you have x minus 2 raised to the third power times x plus 1 squared times x minus 1. Okay? Well, the cool thing about having these factors is if I set each of these factors equal to 0 and solve for x, I will know where my x-intercepts are. Okay? And so according to this one, x minus 1 equals x. Solve for x, then you have one x-intercept at positive 1, which is right here. Okay? And this degree here, even though it's not there, it would be a degree of 1. So this point has a multiplicity of 1. It just means whatever your x-intercept is, what's the power of that root. Okay? So this factor would be x plus 1 equals 0, and then solve for x, it would be at x minus 1. Well, if you look at this solution, or this x-intercept, instead of hitting the x-intercept and passing through it, it's hitting the x-axis and it's bouncing off. Okay, the reason why it's bouncing off is because it has an even multiplicity. Okay, so this root's multiplicity is a 2. Anytime you have a multiplicity of an even number, it could be, if this was x plus 1 raised to the 4th power or x plus 1 raised to the 6th power, any of those even powers, then what it will do is it will hit the x-axis and it will just bounce off. Okay, it's not going to cross the x-axis at all. Okay, and then notice this one is x minus 2. If I set that factor equal to 0, x minus 2 equals 0, solve for x, I get x equals positive 2. So I would have a x-intercept at positive 2. Okay, and notice how this degree is a degree of 3, this degree is a degree of 1, and Do you see how it's hitting the x-axis and then crossing it? Anytime your multiplicity is an odd number, you're going to hit the x-axis and pass through it, okay? Anytime it's an even number, you'll hit the x-axis and bounce off, okay? We will see, we'll spend like a whole day in class on just exploring multiplicities and all that fun stuff, okay? All right, moving on. Complex conjugate pairs. This one, honestly, we're not going to see it. We're going to look at this and explore this later on in this unit. It will be within probably the next week, maybe 2 weeks. I'll have to look and see how soon it'll take us to get to this. These conjugate pairs terrify students. Okay, and basically what it means is that if you have a imaginary solution, and we'll cover imaginary solutions later on, but if you have one imaginary solution, then you have to have two imaginary solutions. Okay, notice you have A and B are just numbers. It could be a 2, a 3, or 4, whatever. It doesn't matter what they are. They're just numbers. But if you have one solution or one root that's imaginary, then you will have two of them. One will have a positive in front of the I times whatever numbers multiplied by I, and one will have a minus in front of the number times I. Okay, so here is an example of one. I'm not sure if I put this in your notes or if you'll have to write it down. And basically it just says that, notice most students, they'll forget or they won't remember, okay, do the signs need to change here or here? Okay, it always changes in front of the imaginary number, and in this case I is your imaginary number. Alright, we'll get into that later on, but please get this in your notes, put it in your dictionary under C's for complex conjugate pairs, and we'll get to it later on in this unit again. And behavior. We've kind of already talked about this with power functions, and we'll see it again. And it just said what happens to x as x gets like to the far left and to the far right of your equation. The number of bends. This is such a cool thing to do. Go ahead and take a minute, fill all this stuff out, and then I'll talk you through it. So go ahead and pause the video so you can write everything down. There's a lot of stuff to fill out. Oh my gosh. Make sure you get all of this filled out in your notes. Whoops. Did not plan on doing that. Alright. There's, holy cow, a whole lot of stuff. And most of this we kind of already went over in power functions, so I'm not going to spend a lot of time on about the leading coefficient. But let's look at the number of bends. So just a bend is like if you have a quadratic function, this is a bend here, okay? And basically the rule with polynomials is that if you have your let's say your degree is 2. Okay, so if my degree is 2, then the number of bends will be 1 less than that. So what's 2 minus 1? Excuse me, 2 minus 1 is 1. So we're going to have, if my degree is 2, or if I had a quadratic equation, I will have 1 bend. If my degree was 3, then I can have at most 2 bends. If my degree is 4, then I could have at most 3 bends. So you're just subtracting one number from the degree to figure out how many curves there are on the equation. Now, does that mean if your degree is 4 that you have to have 3 bends or 2 bends? No, not necessarily. You could have less, but you can never have more than 3 if your degree was 4. So remember how I said we're going to look back at our graph. So let's go ahead and look back at it. And do you notice how this one is a 4th degree? So I have 1, 2, 3 bends. Now this one, notice it's factored, and so really don't know what my degree is for this equation, but if I count my bends, I have 1, 2, 3, and 4 bends. So the degree has to be 5 or higher. Okay, and this one is actually has a degree of 6, which works. Let's see, quadratic just has 1 bend. Let's see, I think we had cubic functions up here somewhere. Here's a cubic function. Notice with the cubic functions, you have 2 bends. Well, 3 minus 1 is 2. Okay, so it's a pretty easy concept. My students love figuring out the number of bends, and then they can figure out how many curves there are and what degree it is. It's pretty fun. All right, last thing in this video is on the last couple pages you have talks about end behavior, and this is pretty much a review from power functions. You've seen it before, and you've seen this before. Really just the difference from what we've seen before is I had y here instead of f of x, but you guys all know, or you should know by now, that f of x and y are pretty much interchangeable. So on this sheet you have, on the very last sheet, you have a whole bunch of graphs and equations, and you need to match up the equations to and the graphs to the end behavior examples. Honestly, I don't know which one will be easier for you guys to match up. First, I'm just going to go through the graphs. I'll uncover the graph, and then equation, graph, and then equation, graph, and then equation, graph, and equation. Okay. Hopefully, you can match these up on your own and then check your answers. I'm going to go through this pretty quickly. So go ahead, pause. Give this video a pause. Try to match up the graphs and the formulas with the end behaviors first, and then unpause the video. All right. So let's look at this. So as x approaches negative infinity, so the left side of the graph, your y approaches negative infinity. So on the left side of the graph is going down. And then on the right side of the graph is also going down. So if you look at your graphs, both the left and the right side should be going down. Okay, this is one of them. I don't know how many have the both going down, but this is one of them. Well, if the right side is going down, then your leading coefficient should be negative. In this case, that's the equation that's going to be negative. Now, I don't know if that's the only negative leading coefficient. You might have more than one. But how do I know that this equation matches this graph? Because I have only one bend here, so most likely my degree is going to be a 2. Okay. All right, let's look at the next scenario. The end behavior is the left side of the graph is going up, and the right side of the graph is going up. So it looks like I know I will have a even power or degree, and let's look at this one. Both of these are going up, so that's exactly what I need for my graph. Now if I count my bends, I have 1, 2, 3 bends here, so I know my degree should be higher than 3, or excuse me, should be 4 or higher. So let's look at it. Let me move this and get rid of it. And in this case, this is the equation that has a degree of 4 or more. Higher than 3, so, and my leading coefficient is positive, so the right side is going up. All right, next one, I have the left side is going down and the right side is going up. So this will have an odd degree polynomial, and the right side's going up, left side's going down. That matches. I have 2 bends here, so most likely my degree is 3. Let's delete that. So notice with these equations, you just have your leading coefficient in your first term and your last term, but really the last term really doesn't tell you a whole heck of a lot about your graphs. You really just need this first term here, your leading coefficient with its degree polynomial. Okay, last one. Left side is going up and the right side is going down. That's going to be an odd degree polynomial. I absolutely love this graph because of how many bends it has. It has 1, 2, 3, 4 bends. So my degree should be at least 5 or higher. Let's see if I can delete that, and there we go. And yes, it's a degree of 5 or higher, and the right side is going down, so the leading coefficient needs to be negative. All right, I know this video was probably a little bit longer than you're used to, but hopefully you watched it all in class. And get all these notes filled out. This last page here, let me see. This last page here with the end behaviors, it's a pretty big page. If you want to try to put it in your E's, because end behavior starts with E, you can, but I think it would probably fit better if you just put it in, have this be the first set of notes in your Unit 4 notes. All your other terms, go ahead and cut them along the dotted lines and put them wherever, in whatever section that the first letter is. So number of bends would, I don't know. I don't know if you will remember if you put it in N better or B for bends. Maybe you might want to go ahead and put this one in your Unit 4 notes as well, instead of in the vocabulary terms. So number of bends, put that in your Unit 4 notes instead of the dictionary portion. End behavior can go in the dictionary portion. Conjugate pairs can go with the C's. Let's see what else. All these others, just go ahead and put them in the dictionary. Minimum and maximum values, we've covered that already. If you wanted to, take these kind of on top of the other notes that you have, but so that you can flip them and see the other notes underneath. Let's see, what else do we have? Yeah, all the rest of this can go in your dictionary portion. All right, I am done talking and I'm signing off. See you guys Monday. Bye.